Hello and welcome back to Math Class in Session. Today, operations with radicals. What is a radical? Well, in math class, a radical is not a revolutionary person. No, no, no. A radical is one of these root signs. This is a radical. An entire radical, well, it doesn't have a non-trivial coefficient in front of it. There's a 1, but it's not written. Mixed radical has a non-trivial coefficient in front of it. 2 root 7 means 2 times root 7. The radicand is the part underneath the root sign. So in the above instances, the radicand was 7. Whatever the number is being subjected to the radical, it's called the radicand. We're working on vocabulary here. An index, well, there's this little number that's tucked underneath that radical symbol right there. That number, that 3, is called an index. It tells us which root of 8 to take. Now, up to now, all the indices have been 2. For example, the square root of 9 is 3, and you don't have to write the little index 2 because it's understood. But in the example here where we're taking the third root of 8, we want the number that, when used as a factor 3 times, gets us to the number 8, and that's the number 2. The number 2, when used as a factor 3 times, gets us to the number 8, because 2 times 2 times 2 is 8. This is what an index means. The square root of 9 means the number that, when used as a factor twice, gets me to 9. That's what a square root is. 3 times 3 is 9. So we have root 9, and we've got third root 8 is 2. The next thing you'll need when working with radicals is going to be some comfort level with perfect square numbers. I've listed the first 10 perfect square numbers here. Observe the ones on the right. 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on. Now, as a math student, if you're studying the subject of mathematics and you need a calculator to find out what 7 squared is, then I've got to tell you, as a math student, you are somewhat crippled. You are disabled. A math student needs to know that the number 64 is 8 squared, that the number 81 is 9 squared, and so on. Because we're going to use these facts. Example, simplify radical expressions. Root 75 as an example. We're going to simplify it. So what we'll do is we'll reference our list of perfect squares and can look for one that goes evenly into 75. And we realize that 25 goes evenly into 75, so we can break it out like this. It's root 25 times root 3, because 25 times 3 is 75. Now, root 25 is a comfortable number that we know. That's the number 5. So we can write root 75 as 5 root 3, because we break out a perfect square factor out of the 75. And this is the principle. Root 20, we look for a perfect square number that goes evenly into 20. And we realize that 4 times 5 is 20. So we'll say root 20 is root 4 times root 5, and root 4 is a number that we know. It's the number 2. So we can write root 20 as 2 root 5. And this is simplifying radical expression. Let's try another one. Root 72. Okay, root 72. We have to check and see if we can find a number that goes evenly into 72. That's a perfect square. And we realize that 36 goes evenly into 72. So we'll break it out, root 36 times root 2, and root 36 is the number 6. So we have 6 root 2. All we're doing is taking the square root 36 and turning it into what it actually is, the number 6. Now, it's also possible to take root 72 and not notice that 36 goes into it evenly and say, yeah, I know my times table is 9 times 8 is 72, and 9 is a perfect square. So we could break out 9 times 8 is 72, and root 9, of course, is 3. But then we'd have to look at 8 and say, but wait a minute, 8 breaks down further because 4 goes into 8. So we could say root 8 is actually root 4 times root 2, and root 4, of course, is 2. And now we'll multiply this. 3 times 2 is 6, root 2. And so in this way, if you don't notice the bigger one, you can take it out in pieces. We took out root 9, then we took out root 4. And we might notice that 9 times 4 is 36. So we took the perfect square factors out in this case in pieces. Of course, we got the same answer, 6 root 2. Root 245, again, a person who's comfortable with numbers a little bit, and numbers don't have to be little numbers, they can start to grow and get a little bit bigger numbers. Root 245, for example, is going to be 5 times 49, or 49 times 5, and root 49, a number that we know, is 7. So root 245 is 7 root 5. You could be suspicious that 5 goes in evenly here and divide it out on a calculator if you needed to. Multiplying and dividing these expressions? Okay, the idea is the coefficients multiply by each other and the radicands multiply by each other. But never does a coefficient multiply by a radicand. So in this instance, it'll be 5 times 2 is 10, root 18. And the root 18 breaks down because it's root 9 root 2. And we have root 9 is actually 3. And now we can go 10 times 3 is 30 root 2. Here we have a binomial multiplied by a binomial. We'll have to pay attention to the little arrows, which I haven't typed in, but let's pay attention to the little arrows here, the distributive property, if you will. So we'll have to say 7 root 2 times 5 root 2 will be 35 root 4. Then we'll say 7 root 2 times root 6 is 7 root 12. And then minus 3 root 5 times 5 root 2, multiplying the coefficients, will be minus 15 root 10, and so on. And then our task is to break down the radicals, the radicands, and see if we can find some perfect square numbers that go in. Well, root 4 is easy, that's 2. And root 12, that breaks down to 4 times 3. And root 4, that's easy, that's 2 again. And so we can say 7 times 2 is 14 root 3. 35 times 2 is 70. And we can't do anything more with this because the radicands don't match. You can't join together radicals unless the radicands match. Let's square one of these things. Well, when you square an expression, we'll have to square the 5 and square the root 3. So it'll be the coefficients times each other and the radicands times each other. And root 9, of course, is 3. There'll come a time soon, I hope, where you see root 3 squared as the number 3. Because every time we square a radical, we simply toss away the radical. So root 3 squared, root 3 times itself, is just the number 3. So a lot of people skip these two steps in between. They just say 25 times 3 when they see this. Squaring a binomial. Yes. Okay, it'll be the first term squared, double the product, and the last term squared, of course. First term squared will be 4 times, well, root 25. I'm quite happy if a student says 4 times 5 right away, because we're squaring a radical, so we'll toss away the radical. Double the product, so it'll be minus 12 root 5, and then, of course, plus the square on the end. Joining them together, this is 4 times 5 is 20, and 20 plus 9 on the end. 29. So we can square binomials, we can square mixed radicals, we can use the distributive property. We're multiplying and dividing. How about conjugates? We've got 3 root 7 minus 2 times 3 root 7 plus 2, multiplying the conjugates. That'll have to be a difference of squares. Product of conjugates here is a difference of squares. It'll be 9 times 7 minus 4. You see how quick this can be when you see the patterns? These are conjugates. So it'll be a subtraction of squares. When we square this, it'll be 3 squared, which is 9, times root 7 squared, toss away the radical. So it's 9 times 7 minus 4. And then do that math. 9 times 7 is 63. Subtract 4 is 59. Dividing radicals. Well, they divide kind of like they multiply. We'll divide the radicands. 48 divided by 6 is 8. 8 breaks down. 4 times 2 is 8. And root 4 is 2. So root 48 over root 6 is 2 root 2. And we're working with these things. Let's go again. 15 root 50 over 5 root 2. Note, we'll not go root 50 over 5 because that would be dividing a radicand by a coefficient. We just don't do that. We'll do the coefficients, 15 over 5, and we'll do the radicands, 50 over 2. So it'll be 3 root 25, and root 25 is a number that we know. 5 times 3 is 15. Root 9 over 2. Well, just as we took this expression and broke it, we can take this expression and break it. Root 9 over 2 is root 9 over root 2. Now, root 9, of course, is the number 3 over root 2. And this is pretty good. But often, usually, math people like to get the radical out of the denominator. Now, I see a root 2 in the denominator. To get it out, we multiply top and bottom by the radical we see in the denominator. Because we know that when we multiply a radical by itself, we can toss away the radical. This becomes 3 root 2 over 2. And that's called rationalizing the denominator. Let's go again. 6 plus root 18 over 3. Well, just as we can add fractions, we can unadd fractions. This is 6 over 3 plus root 18 over 3. But root 18 is 9 times 2, so root 9 root 2. And 6 over 3, of course, is 2. And root 9, of course, is 3. And these 3's will cancel. And we have our simplified response. 2 plus root 2. Now, math people and science people, they appreciate the fact that we can take an expression which is a little bit complex, and we can simplify it to simply 2 plus root 2. Let's go again, rationalizing the denominator, taking the root 5 out of the denominator, top and bottom times the radical. So this will be 5 root 10 over 3 times 5. The 5's cancel, and we have root 10 over 3. The 5's cancel because they're both coefficients and factors. Now we've got a binomial denominator, and so we've got the little trick. We'll multiply top and bottom by the conjugate. Top and bottom by the conjugate of this radical, because we know that when we multiply conjugates together, we'll get a difference of squares. So we'll go top times top over bottom times bottom, and bottom times bottom will be a difference of squares, and that's going to be rational. And rational means there's no root sign in it. So it will be the difference of squares. 4 times 6 minus root 9, which is 3. So it'll be 4 times 6 minus 3 on the denominator. Simplifying, we have 10 root 6 plus 5 root 3 over 21. Rationalizing denominators. Top and bottom times the conjugate. Top and bottom times the radical we see in the denominator if there's just one term down here. Adding and subtracting these radicals. Treat radicals like variables and then collect like radicals, just like you would collect like terms. Here's an example. We need to add and subtract. Okay, well, none of the radicands match. We got a radicand of 12, we got a radicand of 18, we got a radicand of 27, we got a radicand of 8. But they can be reduced. And it becomes this. 2 root 3 plus 3 root 2 minus 3 root 3 plus 2 root 2. I put this line in brackets. This is how we got this, because we took the root 12 and broke it into 4 times 3 is 12. 18 is 9 times 2. 27 is 9 times 3. And 8 is 4 times 2. I'd like you to notice that 18 is also 6 times 3. But neither 6 nor 3 is a perfect square number. So that's why we chose root 9 times root 2. Lots of people, I put it in brackets because soon you too will do this in your head. Root 12 will be 2 root 3 right away. Root 12 will be, you'll think, and you'll go 2 root 3. Root 18, you'll think 3 root 2. Root 27, you'll think 3 root 3, and so on. Now, we have some radicands that do match. We've got 2 root 3's minus 3 root 3's. We've got 3 root 2's plus 2 root 2's, which makes 5 root 2's. And 2 root 3 minus 3 root 3 is minus 1 root 3. Let's do this all again. Break down the radicals. So we have 4 root 3 plus, this is the part that you might do this part in your head and arrive here right away. It's possible. Root 20, of course, is 4 times 5, and root 4 is 2, and 3 times 2 is this 6 that we see. Root 12, of course, is 4 times 3, and the root 4 is 2, and the 2 cancels with that 2, leaving minus 3 root 3 right here. 9 times 5 is 45, so 45 is root 9 root 5, and the root 9 is 3, and 6 times 3 is 18. As one works with these things, you become more fluent in this language. Pause the video if necessary and observe this example. We have some like radicals now. We've got 4 root 3 minus 3 root 3. That'll be 1 root 3. We've got 6 root 5 plus 18 root 5. That'll be 24 root 5. Treating the radicals like variables.